What I have here is a solenoid. So you can see that here, and it's got an iron core in it just to make the magnetic field stronger. But it's basically, once I turn on the current, this is going to turn into a magnet, right? It's an electromagnet because it works when the current flows through it. It's not a permanent magnet. So now something even more interesting is what happens when you put a coil connected to a light bulb. So actually the current that is flowing here, it's an AC current. I'm going to simplify this when we do an example. I'm going to simplify this and assume that it just, when I turn on the switch, the current just goes up to a certain value and stays there, which is not exactly what's happening here, but the physics is the same. It's Faraday's law. But so this current is AC, which means that the field, it's going up and down, right? This is north sometimes, this is south pole sometimes, and it just keeps oscillating like 60 times in a second. So if I bring this here, there will be continuously, and I put it here, there will be continuously a flux going through your coil, and that flux will be oscillating like this. So you would expect that there will be an induced current flowing in one way and the other way and one way and the other way, right? And that current can light up a light bulb. Okay, it's strong enough that you can use it to light up a light bulb. So there's no battery here, of course. It's just electromagnetic induction. So let's assume that we have a coil that is sitting on top of another coil to which I'm going to turn on some current. So the setup is something like this. So a coil sitting here, and then another coil down here. And I'm going to connect the bottom coil to some battery. So I'm going to have the current flowing on the bottom coil this way when I close the switch. So I have a switch here connected to a battery, and that battery is going to have a positive side here and a negative side here, and that is a switch. Okay. So when the switch is open, of course, there is no current flowing in the bottom coil. So you would expect no current flowing in the top coil. Nothing is changing. There is no flux going through the top coil. So there should be no induced current in that coil. Now what happens when you close the switch? As soon as you close the switch, what's going to happen to the flux going through that coil, through the upper coil? So the bottom coil is going to generate a magnetic field. In what direction is that magnetic field generated? So I'm closing the switch, and the current is now able to flow that way. So the magnetic field produced by that coil points in what direction? So the magnetic field points down. It goes down this way. And those magnetic field lines are going to intersect the coil on the top. So the flux going through the upper coil is going this way, right? And it was initially 0. As soon as you close the switch, it starts growing very quickly to some final value. So that means that the flux is growing in that direction. So your delta phi goes in that direction. So if your delta phi goes in that direction, your induced magnetic field is going to have to point in the opposite direction. So the induced field, I'm going to draw it with a different color. So the induced field is going to have to go this way. If the induced magnetic field goes that way, in which direction should the current flow on the top coil to produce an induced magnetic field that points up? So you use your right-hand rule, right? You make sure that the fingers are inside the coil and pointing up on your paper, right? So that means that the current has to be flowing this way. And that is the direction of the induced current. Now, if you think about the polarity, the poles, the magnetic poles of these coils, let's see how they are according to the currents that are flowing through them. The bottom coil has a current flowing that way with a magnetic field coming this way. So that means that this is the north pole of the bottom coil. And that means that the top part of the coil, on top of the coil, that will be the south pole of that coil. Now notice the magnetic field of the top coil, which is the blue lines. So it goes this way. Where is the south pole of that coil, of the top coil? At the bottom, right? Because that side of the coil is the one that receives the magnetic field lines. The magnetic field lines are coming in through the bottom. So the south pole of that coil is pointing that way, and the north pole is on the top. So now you can see what's going to be the magnetic interaction or force between those two coils. Because the south pole of the bottom one is facing the south pole of the top one. So while there is induction current flowing in the top coil, those two coils are going to repel each other. As soon as I turn on the current and the current starts to grow from 0 to a certain value, they're going to repel each other. Okay? What would happen after some time has passed? Assuming that you have a battery there, that you close the switch and you let things reach some equilibrium. So the magnetic field that is going through the top coil, it would have reached a certain value. The current flowing in the bottom coil would have a certain value that is constant. It's not going to change. It will depend on the EMF of this thing and divided by the resistance of the coil. So it's going to reach that constant value that doesn't change anymore. If the current in the bottom coil doesn't change anymore, then the flux going through the top coil does not change anymore. If the flux does not change anymore, then there is no induced current in the top loop. So there will be no force between the two, and the loop will not be repelled by the bottom one. But what happens when you open the switch again? So you let the things reach some equilibrium, and then you open the switch again. So what would you expect to happen, or what kind of force would you expect to have between the two loops? So there is a magnetic field flowing through the bottom loop, so the magnetic field lines are in red there. The flux through the upper coil is what you see there, is pointing also down. But because I open the switch, that flux is going to go away. So the delta phi is going to be pointing in what direction? You have phi is a vector and it's pointing down, and then it starts to shrink. It starts to become smaller and smaller, right? So that means that your delta phi, it's going to be pointing up. Right? So if your delta phi points up, your induced magnetic field is going to point down, right? Because they go opposite to each other. So now I know that the top coil is going to have a magnetic field that points down, that goes through the coil in this direction. Right? So the magnetic field lines are going like this. In what direction is the current flowing in the top coil if the magnetic field is going down? Right? So now, if you use your right-hand rule, and you put your fingers in the middle of the coil, your thumb is going to be pointing along the loop in that direction. So this is going to be the current now, the induced current. And one last thing to check, are these two repelling or attracting each other? So the induced magnetic field is pointing down, so that means that that's the north pole, the side from which the magnetic field lines come out. This is the south. This guy still has the same magnetic field lines pointing down, so that is the north pole, and this is the south pole of the bottom one. So now north is facing south, so the two coils are going to attract each other, right? So when you just connect the switch, they're going to repel, but after a while, if you bring the coil down and then you disconnect the switch, they're going to be attracted.